Hello, welcome to Dynamic Eigenmodes Part 3, Application to Flutter Prediction and Linear Time Varying Systems. Sean Siddiqui, myself, will present Flutter Prediction, and John T. Kim will present Linear Time Varying Systems. If you have not yet watched Parts 1 and 2 of the Dynamic Eigenmodes series, please watch those, as this will contain only applications of the theory previously shown. Aeroelastic flutter is a dynamic instability which may occur with any elastic body with air flowing past it. Flutter occurs at a particular dynamic pressure where the small oscillations of an elastic wing fail to be damped out and an onset harmonic motion is observed. Increasing the dynamic pressure further, the fluid will have a negative damping effect on the wing structure, tearing it apart with large deformations. Understanding of flutter is critical to the design of aircraft, which may be destroyed or lose control of flight due to flutter. In addition to flutter, a related flow-induced vibration is the limit cycle oscillation, or LCO. LCO is a nonlinear phenomenon, whereas flutter is linear. Although in the vast majority of engineering scenarios, linear stability analysis is sufficient for designs, there exist FAA and JAA regulations for both flutter and LCO to be removed from aircraft. For both pose a grave risk to the stability of flight. Please see the Aircraft Design Aircraft Flutter Testing video on Educational Video Library channel. This shows the Aero transonic flutter tests at MIT. This will be linked in the description. Existing flutter testing methods include the following: damping extrapolation, Zimmerman-Weisenberger, envelope function, ARMA, and flutterometer. These testing methods are accurate near the flutter point. However, they lack predictive power away from the flutter point because fundamentals of the fluid structure interaction are lacking. Furthermore, flutter must necessarily involve multiple structural degrees of freedom. Beyond the airfoil pitching and plunging, we must also include bending, torsion, coupled bending torsion modes, and more structural degrees of freedom. Here various flutter test results are plotted. As we can see, the flutter test methods are accurate only if the flutter test points were close enough to the flutter point itself. To reiterate, this was because none of the methods have attempted to capture the full physics of flutter, which is FSI, or the fluid structure interaction. The flow field plays an active role in the onset of flutter. Damping decreases dynamically as the pressure increases. Consequently, system mass, damping, and stiffness matrices will change, eventually to the point where dynamic instability is incurred. From this perspective, it is a parameter variation due to the changing dynamic pressure, which onsets flutter. We will demonstrate how dynamic eigenmodes may be used for flutter testing, which first emerged in the study of linear systems with parameter variation. Furthermore, dynamic eigenmodes will not only allow us to predict the dynamic pressure where flutter occurs, but the exact flutter modes, another novel result of the dynamic eigenmodes, which are invariant under parameter variations. Given a statically nonlinear, dynamically linear aeroelastic equation of motion, x to the n plus 1 is equal to a of qd m infinity times x to the n, where qd is the dynamic pressure and m infinity is the Mach number, and a is the aeroelastic matrix containing all system parameters, including the dynamic pressure and Mach number. The equation overall is a first-order ordinary differential equation, yielding the n plus 1 time step under the action of matrix A on the current state at time n. For our purposes, we will fix Mach number and change only the dynamic pressure. This is the so-called CMVA, or constant Mach varying altitude approach, frequently practiced in industry today. If we want to check for a different Mach number, we repeat the analysis for the new Mach number. In this case, the nominal and perturbed solution each satisfy the following equations, nominal and perturbed respectively. Given these nominal and perturbed equations, we may reason that the stability of the system will only depend on the perturbed equation if we define delta Qd to be Qd minus Qd naught. Assuming the aircraft is stable at the nominal dynamic pressure, flutter will be determined by the dynamic instability of the perturbed system. Here we have stated explicitly the parameter variation due to the change in dynamic pressure to construct delta A. Note that the rank of delta A is twice the structural degrees of freedom. Converting the structural dynamic equation from second order to first order doubled the size of A, and the perturbed system stability depends entirely on the delta Q, as Mach number has been fixed. Dynamic eigen decomposition of a transfer function of the perturbed equation from x naught to the n to delta x to the n plus 1 is written as follows, where lambda prime of omega are the dynamic eigenvalues. It can be seen that dynamic eigenmodes are invariant under the parameter variation due to the dynamic pressure delta Qd, and dynamic eigenvalues are given explicitly by the equation star, relating dynamic eigenvalues at Qd naught and Qd. For a stable nominal aeroelastic system undergoing a change in dynamic pressure, K delta Qd, we may draw a Nyquist plot and adjust K as needed. The stability criterion here is the determinant of I minus K lambda prime omega must avoid encircling the origin of the complex plane. Once K is large enough to cross over into encircling the origin, like the cardioid on the right, the system is unstable. Before that, the system is stable, like the figure on the left, which does not encircle the origin. With this Nyquist stability criterion, we find the flutter condition at a critical Kf, for which determinant of I minus Kf lambda prime is equal to 0, which will just encircle the origin. The critical frequency, omega f, is the flutter frequency. In addition, Vf, the dynamic eigenmode corresponding to the critical frequency, omega f, is the flutter mode. Thus we have obtained all information about the flutter solution from a frequency response at a nominal point prior to flutter. To reiterate, the nominal solution may be any one prior to the flutter, as the dynamic eigenmodes do not change with Qd. So flutter has been predicted by capturing the full physics of the problem, rather than extrapolating close to the flutter point. The flowchart shows how the flutter prediction method works in practice. Nominal frequency data is received in the form of the transfer function g0, and perturbed data in the transfer function g1. Both are then used to construct the dynamic eigen decomposition. The determinant I minus k lambda prime of omega is adjusted by scalar factor k until Nyquist stability criterion is reached at determinant of I minus kf lambda prime of omega f equals 0. Then the flutter solution is obtained. Demonstrating the flutter prediction method numerically, the Goland wing finite element model was used. The Goland wing has a 20-foot length, 4-foot chord, 2 layers of shell elements and a bar element with concentrated masses at grid points. The skins, or shells, and bars provide torsional and bending rigidity. We observe for a Mach number of 0.7, regardless of nominal or perturbed dynamic pressure. We can predict the flutter dynamic pressure, 209 slugs per foot second squared, as long as the nominal condition is stable. On the top, we find the Nyquist plots for Qd0 equals 47.5, Qd1 equals 52.3, and on bottom, Qd0 equals 95, Qd1 equals 104.5. On the left, we are seeing the full plots, and on the right, we zoom in on the origin to see just where the origin is encircled, meeting our Nyquist stability criteria. Continuing the Mach number 0.7 Goland wing example, once we have the dynamic eigenvalue at the flutter, The Flutter mode is the dynamic eigenvector which corresponds to it. Here we see the real part on the left and the imaginary part on the right of the Flutter mode shape. To reiterate, the dynamic eigen decomposition result was predicted with data prior to the Flutter point. We see close agreement between the DED and the RFA, or rational function approximation, which is a standard method in Flutter analysis, indicating DED has captured elements of the multidimensional fluid structure interaction, giving it predictive power not observed in previous Flutter testing methods. Furthermore, if you have questions on why the Flutter mode is complex rather than real, this is due to the aeroelastic damping, as it moves as a traveling elastic wave through the wing. This is opposed to a conservative force which produces a purely real mode, or a standing wave.
It is time to talk about how the concept and mechanism of the dynamic eigenmodes can be applied to linear time varying systems. As you have noticed, all the applications until now have been for linear time invariant systems where the system properties do not change with time. We'll deal with the linear equation in multidimensional state space with parameter variations, except that the matrices are no longer constant but vary with respect to time. As before, we begin by splitting the total solution into nominal x0 and perturbed delta x, creating the nominal and perturbed equations. The nominal equation is not very important, so we'll focus on the perturbed equation. To convert the perturbed system to frequency domain, we take the Fourier transformation of the equation. Since a and delta a are functions of time, and they are multiplied by another time function x of t, a special care must be taken. Recall that a multiplication of two functions in time domain is transformed to frequency domain as a convolution between the Fourier transformations of the two time functions. Furthermore, given n+1 sampling frequencies, we can approximate the convolution integral as the new linear matrix equation shown in the bottom. Notice that the size of the equation is now 2n+1n times 2n+1n, and it is 2n+1 times bigger than the case for linear time invariant systems. However, except for the increased size, this equation looks very similar to the linear time invariant case. Here are the definitions of the matrices that show up in the convolutionary Fourier transformation. Solving for the perturbed solution delta var x of omega, we get the following equation in the top, which depends on the so-called convolutionary transfer function matrix. Again, apart from the matrix size, this expression is the same as the transfer function matrix derived earlier in part 1 and 2. Hence, we can take eigen decomposition of the frequency-dependent matrix to express in terms of new sets of dynamic eigenmodes v var sub nu of omega and dynamic eigenvalues lambda var sub nu of omega. We can see that despite the bigger size, this formula looks exactly the same as the one we had before for the time invariant case. We are now ready to derive a new modally equivalent perturbed system for the linear time varying system. Using the analytic function f of lambda is equal to lambda divided by 1 plus lambda, take the matrix function of the convolutionary transfer function on the previous slide yielding a new equation as follows. If we compare this expression with the eigen decomposition of the convolutionary transfer function, we see that the two systems share the same set of the dynamic eigenmodes, and therefore we conclude that they are modally equivalent. On the other hand, the dynamic eigenvalues of the two systems are related to each other exactly the same way as for the time invariant case. Finally, converting back to time domain, we obtain the maps for the time-varying systems as follows. Notice that the perturbed system matrix delta A of t disappears from the homogeneous part and shows up only in the forcing term of the right-hand side. The upshot is that whether the system is time-varying or not, the maps takes the same form. Equally important, what we have derived here paves the way for the upcoming application to nonlinear systems. This is because, in a nutshell, a nonlinear system can be thought of as time-varying, except that its functional dependence on the solution is nonlinear. This completes part 3 of our video presentation on the dynamic eigenmodes. We decided to do another video to discuss about the nonlinear application. We hope to see you again in the next and final part of our video presentations. Thanks for watching the video.